It's my pleasure to introduce today's seminar. The speaker is very well known to us, Elena, and now the topic seems to me is very interesting. It's Jean's theory in post-Newtonian approach. So please, it's yours.
I'm grateful for your presence here today. Thank you very much for your coming. I would like to say first that I'm not a narrow specialist in statistical physics applied to astrophysics. We made this work in a large group where powerful statistical physics are present. So if I will not be able to deeply explain something, I have all literature, all links and everything just to help you to get deeper in the theme of my talk. But it is you know, maybe as astrophysicists, you all should know that many questions concerning the evolution of stellar systems, of big stellar systems like clusters or maybe elliptical galaxies, after some time includes the statistical period when all stars are formed, and then some statistical statistics governs the evolution of such objects, which we at that stages can treat as a gas of stars. And all statistics as an ideal gas of ideal fluid, all statistics to such systems can be applied like in hydrodynamic limit or something like this, and we can write Boltzmann equations, Euler equations and so on, and to obtain some collective effects which can be measured then from observations. So the motivation is to spread some light on the topic, and our special point is to take into account not only usual potential motion of and potential part of gravitational field, but also its transversal part. So we are just going to take into account the anisotropic pressure and so-called like analogy of turbulent motion of stars. The word turbulence is oftenly or mostly associated to quickly moved systems, but in our case this is like an analogy. This like a model of ideal liquid. As far as it has no viscosity, so any transversal motion of stars become like vertical, because there is no viscosity which would cause laminarity of flows within the star system. So we would like to take into account the turbulence in motion of stars and anisotropy of pressure. We would consider a very big cloud of stars, which is idealized. So it is homogeneous, isotropic, very big, and averagely in stable state. And we would like to investigate little oscillations from average equilibrium, and we would like to derive the equations which describe these little acoustic oscillations of the system. So let's reach further and start with some background, basic theory. Here we have a Boltzmann equation. This is collisionless, so we have this very oftenly used approximation that we have a collisionless Boltzmann equation. That means that our stars do not interact with each other and move relatively freely in self-consistent gravitational field. That is averagely is like 0, but it has second correlations moments through the space. In such situation, we would use one particle distribution function which depends on position in space and on like phase space. It also depends on velocities of every particle, and of course at every moment of time the system somehow evaluates. The force of gravitational interaction will be expressed in terms of momentum flux density of the gravitational field, which form is represented here, and this is a rather standard form. It was taken from this work, and it is possible to see therein other links how it will be explicitly how it can be explicitly derived. So we use this form, which is already written in first order post-Newtonian approximation. What does it mean? Many of everybody know that. It means that we have slow motion and we have weak gravity. So this is our assumptions. These are our assumptions. These are components of vector describing the gravitational field strength. What do we neglect? We neglect the orders, or the high orders of relation of velocity to the velocity of light, and also the derivatives of the Newtonian potential and gravitomagnetic, so-called gravitomagnetic field. So these effects which concern the rotational motion. These are neglected in the first order post-Newtonian approximation, and we take into account that this vector is not potential. So
it means that
yes,
it is not minus gradient.
Yes. It is impossible to express it in that manner. So if we use these definitions and rewrite the Boltzmann collisionless equation, and if we introduce the averaging over the phase space, and we introduce the mass density like that, integrating over the velocities, and the mass velocity, so the velocity belonging to the spatial particle. So we would use these definitions and take the first correlation and the second correlation moments of the by standard procedure of this equation, of the Boltzmann equation, using these definitions. So we will obtain the following system of equations. It is known, this is standard procedure, and where these equations are well known. This is Euler equation, this is continuity equation, and here is the total momentum flux density of the whole system. It is seen here that the total momentum flux density of the whole system is expressed completely through the second correlation moment of the gravitational field strength. You can see it here. This one term includes the transversal is due to the anisotropic pressure is taken into account. So we have following system of Jeans equations. Some definitions here are written written lower. This is the first correlation moment of velocities. It is expressed through the mean value of this product. It is standard definition of the first correlation moment. This is velocity dispersion, just mean value of this product, which describes the average, which describes the deflection of velocity from the mean value. This is the second correlation moment of the gravitational field, and this term from the definition of the second correlation moment of velocities contains the following value, which is analogous to the which is the stress tensor which describes the anisotropic pressure, and this corresponds to the Reynolds stress tensor in theory of turbulence. It is possible to find the corresponding equations in the Reynolds theory of turbulence. So we would use the following equilibrium constraints. Here we see that in equilibrium the following statements are true, and we would multiply our Boltzmann equation by this product and then obtain the following temporal equation for the second correlation moment of velocities. This is expressed through the correlation moment, third correlation moment, which can be expanded as follows, where the equilibrium values of this moment are taken, which are defined as follows. These are the constants. Inputting this expansion into the previous equation, we would obtain the following equation for the second correlation moment, and the second task is to derive the equations for the second correlation moment of gravitational field strength. For this purpose, we use the Einstein equations, which are written in Maxwell form, and this method is very well explained in this paper, and they also have citations of other earlier paper, but this is brief and very clear to my opinion. The procedure how to obtain the Maxwell equations in Einstein equations in Maxwell form, and we neglect all the terms which do not satisfy the first order post-Newtonian approximation. Here I just stressed that we have weak gravity and slow motion, and this means that such derivatives are much bigger than temporal zero. This means the derivative with respect to time. Greek indices means our four-dimensional space, as usually in general relativity. And Latin indices means the only spatial nz's, just spatial coordinates. So the spatial derivatives of, this is the metric, which is mostly Minkowskian plus very small corrections, in which is standard representations for post-Newtonian expansions. So we have these corrections are much less than 1. These derivatives are much more than time derivatives of the corrections. And we use, from this work, we will use the definitions for so-called gravitoelectric and gravitomagnetic field. This is the strength of the gravitational field expressed through the derivatives of the metric tensor. introduced here, and this is so-called gravitomagnetic induction of the gravitational field. It is expressed in standard form also through the derivative of such non-diagonal components. Well, then we obtain the following, inputting all that in our inputting on that in our genes system. We will obtain, just a second, I will clarify how namely it should be done. Yes. So this follows from the Einstein equations. They give the following temporal equation for it also taken from this work. It was derived there very clearly and straightly, and we see the following equation for the gravitational strength field, which also involves the gravitomagnetic field. And further, we would like to use the following definition. First, we would like to switch to the entire co-moving system of reference, which moves with velocity v at every point of space. So we just exclude some systematic external gravitational field. It should be zero, and this field appears only due to the motion of particles with velocity v in the Newtonian gravitational field. The components of Newtonian gravitational field are expressed by definition as follows, and then inputting all that to just a second, we should multiply something by something. Here I have written that. Yes, the previous equation should be multiplied. Should be multiplied by another one here. Should be multiplied by another one metric component, gravitational field strength component at the same point, and then we symmetrize by indices, by tensor indices, and we will obtain the following expression. This expression is quite similar to the expression for the magnetic induction in Maxwell theory. So we will use the following condition, that in equilibrium we have the following: total gravitational field strength in equilibrium is zero. Gravitational correlation of the gravitational potential, this is just equilibrium value, is constant and expressed through the this value. And then we linearize the obtained equation, just neglecting all terms which are not satisfied to the first order approximation, post-Newtonian approximation, and we would obtain the following expression. This mathematic, I think I should not concretize in details all that, because it was done in many papers, the similar procedure. This is just, the just importance is that this equation includes the correction that appears due to anisotropic pressure and taking into account the transversal part of the gravitational field. Here is Euler equation, which is obtained after linearization and inputting all our definitions. And this is finally the equation for small acoustic oscillations in our system. Well, it seems like a very complicated, but we will apply that to our we will switch to the Fourier transformation, and we solve this equation for small for small acoustic oscillations. And switching to Fourier transformation composition, we just put all that into this equation and obtain the following solutions. This is the frequency of longitudinal oscillations. This is expressed through all our values. This is square mean velocity of, this is gravitational field, the mean value, and this is the equilibrium density of our system. And these are two transversal, because we have three spatial directions. These are two transversal modes of oscillation, of acoustic oscillations. From these frequencies, taking into account that the velocity of acoustic waves is proportional to the square root of that, to the frequency, we will obtain the following expressions for the acoustic wave longitudinal one and transverse one. And we see this is the solution of the obtained equation. This describes how waves, depending on parameters of our system, how they spread out. Yes, and what can we see here? That the one thing that we should say, that if one of these mode turns to imaginary quantity, this mode, corresponding mode, will be increased. And this means that gravitational instability evolves and the stability of cloud breaks down. Well, so from here we can just write the condition of the gravitational stability of our system, depending on which is depending on the velocity of acoustic wave, or depending on the frequency of the oscillations. This is what is the main reason why the gravitational instability arises. So we can notice that this value can be expressed through the transverse one in such a way. And we see if the transverse one becomes unreal, then this does not exist. And this exists always when exists this one. If this disappears and becomes unreal, this one also becomes unreal. So we would say that this is the more strict condition which we will use to obtain the restrictions on the parameters of our system. I would write here this again, and from here we just want it to be real. For this we need this condition to be true, and then using standard definitions of the gravitation, of the density of gravitational energy of the system, this is standardly expressed, and the average kinetic energy of the system, we can write that this restriction, this condition leads to the following condition, that the two kinetic energies should be greater or equal than gravitational energy density. And in the limit, when transversal wave has a zero velocity, it does not exist, we obtain the virial theorem exactly, which was not which was not possible to express, for example, in Chandrasekhar's estimation. I will show it later. So this is the virial theorem, which is standardly used to describe such homogeneous systems. And inputting the total gravitational energy for the spherical cloud of stars with average mass expressed in such a way. This is a globular cloud. It's the density of the total energy, the density of gravitational energy of the cloud can be expressed in such a way from here, and taking the mass, inputting the mass, and from the condition which was derived, we obtain the following relation, which leads to the restriction of the size of the spherical cloud. No, well, what can I say? I can say the following. This is estimation that was obtained by Chandrasekhar, who also included the usual manner to use some corrections to relativistic corrections to Jeans theory. Usually people do not use the anisotropy of pressure. They just neglect these effects. But we see that it allows to make rather well correction, which is in good accordance with the virial theorem. What can we not say about Chandrasekhar restriction? If we just, this is just brief calculation which shows that in Chandrasekhar estimation the virial theorem is does not hold well strictly to say. And here just comparison of Chandrasekhar's results with our results obtained in this paper. We see that results differs by twice as different. It is not so many for estimative value, of course. The further part of our interest was somehow obtain, somehow to apply our results to huge to find something in huge massive of astrophysical data, just to distinguish somehow, do this difference, is this difference can be noticeable or not. In good sense, it seems that it should not be noticed in with accuracy, within accuracy which is usually obtained in some astrophysical observation. But I believe that maybe there are some data already which has a good accuracy, and it is possible to distinguish. What we did here, we just have taken some galaxies which are listed here, the names. These are spherical, these are not galaxies, these are globular clusters, for which the observed mass, they have mass radius and density are somehow measured, and we calculated using our result, this one, we just calculated the mean velocity of the stars of stars within this cluster. Seems not to be a huge bullshit, but but seems to be realistic. But I'm not a specialist in astrophysics, and I would like to obtain some advice from you, or maybe from you can advise to see some literature. Where can I find some data observational to which I could apply in broad range of data, I could apply our results. This is just a picture of different globular clusters, relatively close one, relatively far one, and the middle. And these black points corresponds to this one. We tried to do something with this diagram, but this is just a cubic spline. in logarithmic scale and nothing more we could do, just calculate the velocities, and we did not find the observed quantities for these galaxies. Maybe just it is because of I don't know where to to look, where to look for. So this is a test of our results on some real systems, and this is the end of my talk. If you have any question, please, I'm ready to answer if I could. That's it. Thank you for all my co-authors.